Have you ever looked up at the sun and just wondered how we take that incredible, brilliant light and turn it directly into electricity? It's a pretty amazing process, and it all happens silently inside those flat panels we see everywhere. So let's break it down step by step and see exactly how a ray of light becomes the power for our homes. First off, to really appreciate what we're talking about, we have to think about the scale. It's kind of mind-blowing. The amount of solar energy that hits our planet is just immense. In fact, in a single hour, just 1 hour, there's enough sunlight hitting the Earth to power all of humanity for an entire year. It's this constant, unbelievable stream of power, just waiting for us. And that really is the big question, isn't it? It feels a little bit like magic. You have this flat, silent panel just sitting on a roof, no moving parts, and somehow out comes usable electricity. But it's not magic at all. It's just really, really brilliant science. The secret, the thing that makes it all possible, is a single principle with a pretty cool name, the photovoltaic effect. And if you break that name down, it makes perfect sense. Photo means light, and voltaic has to do with electricity. So it's literally light electricity. That's the science that makes this whole thing go. Okay, so to understand this effect, we need to zoom in. I mean, way, way in, down to the microscopic level, right into the very heart of a solar cell. We're going to look at something called the p-n junction. So at its core, a solar cell is surprisingly simple. You can think of it like a sandwich, made of two very special layers of silicon. You've got a p-type layer and an n-type layer. And these two layers, pressed together, they do all the heavy lifting. Let's think of it this way. The n-type layer, think N for negative, has been treated so it has a ton of extra electrons, just kind of hanging around, ready to move. The p-type layer, P for positive, is the opposite. It's been designed to have a deficit of electrons, which creates these things scientists call holes. They're basically perfect little parking spots, just waiting for an electron to come along. And right where those two layers meet, well, that's where the real genius is. This boundary is the p-n junction, and it creates a built-in electric field. The best way to picture it is as a one-way street, or maybe even a slide, that will force any freed electrons to travel in only one direction. No turning back. So, we've built our one-way street for electrons. It's all set up. Now we just need something to get the traffic moving, right? And that's where sunlight comes into the picture. This quote really nails it. You see, sunlight is made of these tiny packets of pure energy called photons. And when these photons come flying in and hit the solar cell, they transfer all their energy to the electrons that are inside the material. And this image shows that moment of impact perfectly. A photon zips in, bam, it smacks an atom with enough energy to knock an electron completely loose from it. It's like a tiny microscopic game of billiards. The photon is the cue ball and the electron is sent flying. And that one little electron getting knocked free, well, that's everything. That's the whole ball game. It's the photo part of the photovoltaic effect. This right here is the initial spark, the very first step in creating a flow of electricity. But, one free electron isn't going to power your laptop. We need to collect billions and billions of them and get them all marching in the same direction. And this is where that p-n junction we just talked about becomes the absolute hero of the story. This graph shows you the difference perfectly. See that top curve labeled dark? That shows that without any light, the cell does absolutely nothing. But look at the bottom curve, the illuminated one. The moment light hits it and frees those electrons, the p-n junction sweeps them away, forcing them into an organized flow. That creates both a voltage and a current. So once those photons start knocking electrons loose and the p-n junction starts directing traffic, what you've actually created is a power source. At this point, in an electrical circuit, that illuminated solar cell is acting just like a battery. It's ready to push a current through and do some useful work, like charging your phone. Okay, so that's awesome. We've managed to generate electricity from one single tiny cell. But there's a small problem. One cell, all by itself, doesn't really make that much power. So how do we get enough juice to run, say, a whole house? Believe it or not, a single one of these solar cells only generates about half a volt of electricity. Yeah, just 0.5 volts. That is less than a single AA battery, so it's not nearly enough for most of the things we want to power. So what do you do when one battery isn't enough for the TV remote? You connect them together in a series, right? And that's exactly, and I mean exactly, what we do with solar cells. By linking them up one after another, all their individual voltages add up. And the results? Well, When you connect about, say, 28 to 36 of these little half-volt cells together, you get a much more useful 12 volts, which is a really common standard voltage for all kinds of electrical systems. And this is the final product. This whole string of cells, all wired together, encased in a protective frame with some special diodes to keep everything safe, this is what we call a solar module. Or, what pretty much everyone just calls a solar panel. So let's just recap that entire incredible journey one last time. It all starts with a single photon from the sun. It strikes the cell and knocks an electron free. Then our p-n junction acts like a director, forcing all those freed electrons to flow in the same direction. That directed flow is an electrical current. And finally, we combine lots of these tiny cells to create useful, large-scale power. Pretty amazing, right? We go from a single invisible packet of light all the way to a global power source. It really makes you think. If one tiny ray of light can kick off such a powerful and elegant chain reaction, what will our world look like when we get really, really good at capturing all of them?